Hello everyone. Welcome to the third lecture of the fourth module, which is on flash memories. The disclaimers remain the same. Recapitulate what we were covering in the last lecture. So we were discussing about this NOR and NAND flash memory. So NOR and NAND is nothing but architectures in which your floating gate cells are arranged, right? Now, while the NOR flash memory is mostly used for embedded application that is for code storage, your NAND flash memory is usually used for data storage. And you know that for code storage, your memory has to be fast. And for data storage, you can work even with slow memories. So you need to make the programming mechanisms in NOR flash faster as compared to your NAND flash memories. So in NOR flash, we program the floating gates with the help of a mechanism which is channel hot electron. While in NAND flash, we program it using a mechanism which is Fowler-Nodin tunneling. For erase, we use Fowler-Nodin tunneling in book. Also looked at the evolution of program and erase mechanism in NOR flash. So while the program mechanism is CHE itself, what you observe is as the generations or as the technologies improved, what happened was the supply voltages or the voltage at which your CHE mechanism takes place, that kind of reduced. Why so? Because if you scale your gate length, if you scale your channel length and all those things, even your oxide thickness. So scaling kind of, with scaling, you can achieve same level of electric fields at a relatively low voltage, right? At relatively low voltage. So there is not much of innovation in the kind of program process. But if we look at the erase process, so in the first generation, what people used to do was people used to apply a high voltage at the source. And because of this, electron used to tunnel from this floating gate towards this source in what is known as gate on source overlap region, right? And this was Fn itself. The mechanism was Fn. However, if you are applying a voltage such as 12 volts, it will lead to eventual stress and degradation of your device characteristics. So then in the second generation, what people used was, they were still using the same mechanism that still, your tunneling was happening in the gate on source overlap region itself, but now they kind of use dual polarity. So in the second generation, they used what is known as dual polarity. So effectively, they distributed the entire voltage for tunneling between your source and your gate. So they applied a negative voltage on the gate and they applied a positive voltage on the source, and still tunneling was taking place only in this gate on overlap source region, gate on source overlap region. The best innovation came in the third generation when they started using this body terminal. So what they did was they applied a positive potential on the body and they applied a negative potential on the gate. So now the entire channel could be used for erasing. So third generation, that is the use of body terminal for erasing, helped or it increased your area for tunneling, and therefore it increased your speed, erase speed. Okay, and at the same time you see that whatever voltage you're applying on the body has to be applied at the source and drain regions. Why so? So that your source channel or drain channel or channel drain junction doesn't get forward biased. Okay. We also saw that since this CHE mechanism requires a lot of current, so this program process in NOR flash is kind of energy draining or energy consuming. as compared to your Fowler-Northen process in your NAND flash. So Fowler-Northen, the tunneling current is low. So it's more energy efficient. We also saw that your NOR flash is kind of bit addressable. That is, you can actually uniquely access each of these cells because each of them have their independent bit line and source line. If you look at all these cells, they have independent connection to the bit line and source line. Therefore, you can easily kind of access individual bits at one time. However, in the NAND flash, since they are connected in series, only one cell has kind of access to the bit line, and rest all have to work in the pass mode or read mode. So read here is sequential. So let me write it somewhere. So here in your NAND flash, read is sequential. What that means is, suppose you have to read this cell, what you will do is, you'll kind of program you kind of apply to each of these word lines a voltage which is V pass or V read, and that is high voltage. So you'll kind of create an inversion layer over these unselected cells. Why so? So that their contribution to the series resistance, or they offer a low series resistance. And in NAND flash, you kind of read the string current. So each of these cells connected over here form what is known as string. So what exactly is read in NAND flash is the string current. So if these are kind of if these are in pass mode or read mode, what it ensures is that the string current kind of is only a function of the current through this selected cell, and it's not a function of the other cells. So that is why we put all the other cells which are unselected to VPass or VRead mode. Then we also discussed about reliability, and we saw that there are different parameters to gauge the reliability of any NAND flash memory. So one of them was to analyze this threshold voltage distribution. So to analyze the threshold voltage distribution, what we did was, initially we kind of exposed the entire array to UV. So first we did this UV exposure, and then we measured the threshold voltages. So what we obtained was a curve like this. So it simply says that your threshold voltage is Gaussian distributed, or the parameters of these cells are also Gaussian distributed. So UV exposure kind of tells you about the process variation, which is extrinsic parameter. Then what we did was, we kind of programmed each cell using same pulse amplitude and time using CHE mechanism, let's say. And then we again read their threshold voltages. So once we did that, we got a Gaussian distribution which was somewhat wider. So we get somewhat wider distribution. Why it is wider? The reason it is wider is because this kind of, so different cells having different parameters, different channel lengths, different oxide thickness, and different things. So if you apply the same drain voltage, the amount of electric field that they experience will be different. And as such, they'll show different levels of this hot electron production. So because of this, you'll have different threshold voltages, and you'll have different, charges which are being injected into your floating bed, and which leads to different threshold voltages. So this kind of represents your process variation plus intrinsic variation. This intrinsic is kind of physical mechanism dependent. And since it is not changing much, we told that your CHE is kind of relatively immune. Relatively immune to process variations. I won't say that it's entirely immune, because even here you see some kind of increase in the kind of this width of this distribution. And then what we did was, we kind of applied erase pulse, and we did it using the FN mechanism, and then we looked at the threshold voltage distribution. Then what we observed was that there was a huge tail and the distribution was very wide. And then we started talking about two kind of cells. First one, which are called normal cells, which tend to follow, the CHE program kind of pattern, which are like this. So these cells are kind of called normal cells. And the second cells, or second class of cells, are called tail cells. Why tail cells? Because their threshold voltage is very small, which simply means that they get erased very fast. So, and then we concluded that here your FN mechanism is very sensitive to process variations. Why so? Because any tunneling mechanism is exponentially proportional to parameters such as electric field, then band gap, and all those things. So any tunneling mechanism, if you have, there the impact of variation on that mechanism would be huge, just because it is kind of exponentially dependent upon the parameters which define tunneling. Also looked at different program disturbed sources. So if we want to program, let's say, this cell at the middle of this array using, let's say, FN tunneling, then what we do is we apply a high voltage at the gate, right? We apply a high voltage at the gate so as to extract electrons from channel into the floating gate. So once you do that, what happens is, even these unselected cells over here, I mean, we just wanted to program this cell, but even these cells along this row kind of see the same gate stress, right? They see the same gate voltage, same control gate voltage, and as such, some electrons may be injected from channel to floating gate, even in these cells along this row. So this was called what? This was called gate stress, or row disturb effect, or row disturb, I would say. Now, what if we want to program it using CHE? So if you wanted to program using CHE, then what you do is you apply a high drain bias, right? So you apply a high V drain over here, and then what happens? You ideally want this V drain to only get applied to this, but since all cells in this column are actually sharing their drain terminal, so the same drain voltage kind of gets applied to these neighboring cells as well. And because of this, what happens? So if you have a MOSFET like structure, so let's say this is your floating gate and this is your control gate. Let's say this is your drain, this is your source. So what happens is, because of this applied high V drain, some amount of charges which are already in the floating gate, they may, tunnel towards your drain. So what may happen is, we write it. So existing charges in floating gate of unselected cells may tunnel into the drain and disturb the charge state, right? And what is it called? So this is called your soft erase. And where this happens, it happens only in this region. What this region is called? It's called gate on drain overlap region. Okay. Then we were also discussing about retention. How we define retention? So we define retention as ability of your memory, any memory, to retain the state What is that state? That state can be threshold voltage for flash. That state can be resistance or conductance values for RRAM, threshold voltage for flash, resistance or conductance value for RRAM, and so on. The industry standard is if any device can retain the state for 10 years, then it qualifies for industry. Qualifies for industrial memories. Now, in flash memory, what exactly is happening is your floating gate has charges, right? Floating gate stores charges, and your memory state is kind of a function of the amount of charge that is being stored in your floating gate. The problem is with scaling, the gate can scaling. What is happening is the volume of floating gate, which tends to hold charge, that has reduced significantly. So you have a very limited, what is happening? So you have a very limited amount of charges in your floating gate, which is kind of dictating your threshold voltage. Now, if somehow even some of those amongst few charges leak, there can be a data loss. Then we discussed the different, different sources of this leakage of charge. So what are these sources? So it could be because of defects in tunnel oxide. So what is happening inside flash memory? You are continuously, stressing your tunnel oxide by applying high voltages, high electric fields to pass some electrons through it, right? So once you stress it, what it leads to, it creates defects. So these defects may lead to leakage of these charges. How can this be controlled? So you have to maintain a good process control for this. Since you cannot do anything with the physical mechanism, you will have to either apply CHE or FN and then make these electrons tunnel from your channel to the floating gate. That anyway you have to do. Okay. So the second source may be your defect in the ONO layer. Similarly, your ONO layer is also being stressed, but this ONO layer is so optimized, or it's kind of a gift to the memory designers. So we need not do much about it. I mean, the defects that are being produced in ONO layer is already small and it is manageable. So what could be the third reason? Third reason could be this mobile ion contamination. So how does this mobile ion get inside your oxide region? So it's because of your fabrication process. There are these mobile ions like sodium, potassium, which kind of gets injected inside this oxide, and how we can remove it. So we discussed about something which is called this ion gettering process. And if you have a very good process control, then also you will end up injecting less amount of these ions in your oxide region. And the last possible source was the electrons, which are kind of already embedded in your sidewall encapsulation layer, right? How does those electrons come, or where do these electrons come from? So when you are fabricating, you do many processes which involve plasma. So some amount of electrons or ions from this plasma damage the oxide, and these electrons or ions may be even trapped inside these oxide. So later, with time or as you increase the temperature, what may happen is these trapped electrons may be injected into your floating gate. Even electron injection into the floating gate is problematic because it can change your data. So either way, either the charge is being leaked or the charge is being injected. Both are problems for this data. So for this plasma damage also, the best thing to do is you maintain a process control to kind of minimize its impact. So with this, let us now look at how we measure this retention. So the question is how we measure retention. So we saw that industry requirement is kind of 10 years of retention. So do we really wait for 10 years? Do we really, the question is, do we really wait for 10 years and then check if the data is being stored or not? So this is something that the industries can't afford, right? Because the technology changes so fast that if they don't deploy their products in the market, they would be in huge loss. So they can't wait for 10 years to test this retention. Then how do they do it? What is the exact procedure of doing this? So they perform something which is called accelerated tests. So they go for accelerated tests. And what are these accelerated tests? So they kind of, expose their ICs or chips or memories to hostile environment. And why do they do that? Just to mimic the impact of degradation with time or over time. So what they do, they kind of expose the chip to harsh environments. What does that harsh environment means? So they bake or expose the memory arrays or the chips, memory chips, to high temperatures. So high temperatures stresses your devices, and that stress, so that high temperature stress kind of mimics the degradation that one may observe if you leave the device for a large duration of time or degradation over time. And there are certain set standards by the company. They have calibrated their data and all. So for instance, for RRAMs, what they do is, for RRAMs, they kind of heat the RRAM array to 125 degrees Celsius for 10 hours. And then they look at the device characteristics. And then they compare it with as deposited or virgin devices. So heating RRAMs for a period of 10 hours at 125 degrees Celsius kind of mimics a degradation in the CAC. This kind of mimics a degradation that one would see if RRAM is left for 10 years. How they do it? So they use this concept of Arrhenius activation energy. If you want to get into details, you will have to get into several reliability models. You'll have to study about the reliability models. So I won't get into the details, but they kind of look at the Arrhenius activation energies once they expose these devices to very harsh conditions, and that is how they kind of check whether your device will be able to retain that memory state for 10 years or not. Now, with this discussion on retention, let us look at another metric which is popularly used to quantify the reliability of these flash memories or any memory in general. That is known as endurance. So what is endurance? So endurance is kind of defined as the number of consecutive program and erase cycles So you program in one cycle, erase in the other cycle. So it's the number of consecutive program in a cycle that any memory device may tolerate before showing signs of degradation, or before memory failure, or before showing signs of degradation or memory failure. And this number is 10 power 5 cycles for flash floating gate memory. So typically, if you cycle it for let's say 10 power 5 times, if you consecutively program and erase it for 10 power 5 times, then your flash memory quality will degrade, or it can also lead to your memory failure. So what exactly we mean by these things will be clear as we discuss it. So what exactly is happening is, in your floating gate memory, there is this tunneling oxide. So you're kind of stressing this tunneling oxide, and you're passing electrons through this tunneling oxide, right? Mechanism may be CHE or FN, but somehow you are starting with an insulator and you're forcing current through it, you're forcing electrons through it. So once you do that, it can lead to two kinds of defects depending upon your mechanism. So it can lead to two kinds of defects based on mechanism. What are those two kinds of defects? First defect is generation of traps inside your oxide or tunneling oxide. This will happen in both CHE and FN, because at the end of the day, these electrons or this current is kind of passing through your oxide. So it will kind of stress the oxide and there will be trap generation. So let me draw the diagram, then it will become really clear. Let's say this is your floating gate. Let's say this is your control gate. This is your floating gate. And then this is your MOSFET kind of structure. So you have this. Okay. So in both these CHE and FN mechanisms, the electrons tunnel from your channel to the floating gate. While in Fowler-Norton tunneling, they are tunneling across the entire channel. What happens in your CHE is, only the electrons which are highly energetic close to this drain region, these electrons tunnel into the floating gate. So it's only the difference is only in the location of the electrons which are kind of tunneling into your floating gate. So because of this, what happens is this creation of these defects in your oxide region. These defects will be spread throughout. So these traps are spread throughout in the case of FN, and these traps are localized close to the drain region in case of CHE. Okay, so this is one mechanism. So what is the second defect? The second defect is generation of interface states where close to drain surface, right? And this happens only for CHE. So what happens is, since your electrons are moving with very high velocity, so there can be a generation of interface states. Now, how this affects your programming or program meeting? So in programming, what you intend to do is, so let me just write it. So in programming, you intend to inject electrons into your floating gate. Now, if you have these traps over here, or if you have these interface states, let me draw it by another color. Let's say, so at this interface itself, you'll have some interface states like here at the surface. So if you have these interface states, or if you have these traps, what they can do is, these traps in tunnel oxide or interface states in drain, they may capture these electrons. They may capture these electrons, and as such, the effective charge which had to be transferred from your channel to the floating gate, effective charge on floating gate reduces. So effective charge, if that reduces, what happens to your threshold voltage? Your threshold voltage reduces. This is what is seen. So you program your flash and then erase it. So when you subsequently program and erase it, you kind of generate traps with each programming cycle. So as the number of PE cycles increase, so let me explain it. So as your program erase cycle increases, more traps are created, more traps or defects or interface states are created, and they tend to capture more electrons. Since more electrons are captured, the effective charge, which is kind of on the floating gate, given you apply the same programming pulse, that reduces, and as such your threshold voltage reduces. So you see, threshold voltage reduces with the number of program cycles, with the number of program erase cycles. Okay, now what about the erase mechanism? So for erase mechanism, what you want is, you want to kind of inject, or you want to kind of pull out charges from floating gate back to channel. Remember that if they are not pulled back to the channel, if they kind of remain in gate stack somehow, so from floating gate, they should be brought back into the channel. If they remain in the oxide, tunnel oxide, what they may lead to is, they may again lead to shift in threshold voltage. So what you should ensure while erase is, you should bring back all the charges that were on the floating gate to the channel. If somehow some of these electrons are trapped in your defects, if somehow, let me write that as well. So if somehow the electrons are trapped within the tunnel oxide, then that would also lead to VT shift. And the direction of the shift, and let me write here that direction of shift depends on type of trap, which kind of captures your electrons. So what are the possible traps that we have? So we have two types of traps. One is acceptor type traps. So the property of acceptor type traps is they become negatively charged when filled. So if your oxide, tunnel oxide, has got a lot of acceptor type of traps, what will happen is those will kind of get negatively charged when they capture electrons from the floating gate, and then what that will lead to is that will increase your threshold voltage. So if you have a negative charge in your gate oxide, your threshold voltage increases. So this is what is shown here. So if you have acceptor type of traps, which are kind of capturing these electrons during the erase, what is happening is your threshold voltage actually increases. So here what you observe is, due to your interface defects and all these things, interface states and defects or traps, your program VT is reducing. And if you have a lot of acceptor traps which are capturing electrons from your floating gate and not allowing them to go to your channel, your erase VT is increasing. So if this increase or decrease is too much, you can also end up with a case where this is reducing and this is increasing. You can end up to a case where these two merge, and that is called collapsing of memory window or device failure. So when does the device failure occur? When both of these kind of behaviors, I mean the increase in the programmability and erasability, if they are showing opposite kind of behavior, if programmability is reducing and your erasability is increasing, it leads to a reduction in the memory window. So how do we define memory window? So this is called the memory window, the difference between the VT in the erase state and the program state. Okay. So if your difference between the VT, between the erase state and program state is kind of reducing, and it kind of gets intersects, then you can say that your device has failed. So this memory window closure is something, or memory window reduction is something which actually happens. Now there is another kind of trap which is known as donor trap, right? So apart from acceptor trap, you also have something which is called donor trap. So let me log the zoom. So you also have something which is called donor traps. So what is true about donor traps is, so they are neutral when filled and positively charged when empty. So if not all of these donor traps created due to stressing are filled, then it will lead to a positive kind of charge in the gate oxide. If you have a positive charge in your gate oxide or gate stack, what it will do is, it will kind of also reduce the weighting. So in that case, if your traps generated are kind of donor traps and most of them are unfilled, then what may happen is, then even your erasability may go down. So this was the case when your acceptor tracks were kind of dominant. If your donor traps are dominant and most of them are vacant, then it can also lead to a reduction in the erasability. So if both of them are following the same trend, if both the programmability and erasability are reducing, or if both are increasing, that is perfectly fine. But if they are following opposite trend, then there is this case of collapsing of memory window and the memory window reduces, and this is the case when you can say that your device has failed. Now let us answer another important question. And what is that question? Are retention and endurance related? In general, no. But the mechanisms which degrade endurance also degrade retention. So another important concern in flash memory is your retention after cycling. So let me write that. So your retention after program erase cycling is also a concern, major concern for flash memory designers. So what you are essentially doing is you are kind of generating traps within the tunnel oxide. How? By stressing it with high electric fields and forcing current through it, tunneling current or CHE current through it. What may happen is, if you have a lot of traps adjacent to each other, as suppose there's in this energy band diagram, let us say that there's a trap here, there's a trap here, there's a trap here, and there's a trap here. So what may happen is, electrons may tunnel into these traps, and then they may even hop or tunnel from one trap to another. So here what exactly is happening is, these traps are assisting the tunneling process. So these traps are assisting tunneling process. So this process is called trap assisted tunneling, TAT. So what is its implication? Its implication is simple, that your FN is a high electric field phenomena, right? FN takes place only when the field is really high. However, at low electric field, your FN current would be negligible. But what happens here is, just because of this trap assisted tunneling phenomena, we have a large current as compared to the FN tunneling current. We have a large current even at low electric fields, right? And this current at low electric field through this stressed tunneling oxide is higher than the one we theoretically calculate, or than the theoretically calculated value of current for FN tunneling, and this deviation is what is known as stress induced leakage current, or SILC. So what exactly is this SILC? So you kind of stress your tunnel oxide, you generate these traps. Once the traps are generated, you have this trap assisted tunneling mechanism which happens even at low electric fields where FN is not dominant, and then this leads to a leakage current which is known as stress induced leakage current. So now what are the factors on which this SILC depends on? So this SILC depends on mainly three factors. What are those factors? The first factor is your stress field, stress electric field that you are exposing your tunnel oxides to. Then second, it depends upon the amount of charge that you inject during your program or erase cycle. Why so? Because the amount of charge dictates the current that you force through your tunnel oxide, and that kind of dictates the number of traps or interface states that you produce. And the third factor is oxide thickness. So your thinner the oxide, the larger number of traps that will be produced, because it will see a higher electric field. So scaling from SILC perspective is detrimental. Or scaling is kind of detrimental from SILC perspective. As you scale the oxide thickness, your SILC will increase. Now, since this SILC is a leakage mechanism and it's induced due to program erase cycling, since it's a leakage mechanism which happens at low field, it will definitely reduce even your retention. Right? Retention will be reduced because of this leakage which is happening at low electric fields. So if you look at these plots which simply show retention of threshold voltage or retention of charges after different number of cyclings. So when your flash memory is cycled only for like program, when the number of program erase cycles is only 10, most of the cells, so on y-axis you have percentage of cells which have certain threshold voltage, x-axis you have threshold voltage. So most of the cells have like threshold voltage which is high. Only few cells, few number of cells kind of, after t equals to 3 years, kind of leak the charges and have a threshold voltage which is low. However, after, let's say 10 power 5 cycles of programming, 10 power 5 cycles of program and erase, consecutive program and erase, if you look here, only these few cells have their VTs intact. Most of these cells show charge loss or charge leakage. For identical measurement conditions, number of cells showing leaked charges is more when your program erase cycle is high, 10 power 5 in this case. So this simply means that retention after cycling degrades, and it's an important concern. It's a very important concern. And also, as we discussed earlier, this hinders scaling of your tunnel oxide. Why so? Because once your tunnel oxide thickness reduces, your electric field increases, and it can tolerate less amount of stress. There would be more defect generation for the same amount of electric field applied. Now, how can we correct this? So ECC, if there were no ECC, there were no operation of this flash memory. So ECC is one kind of correction measure which can help fix it. And also you can, if you have very good process control of tunnel oxide, you can reduce it somewhat. Then you can reduce it somewhat. You can just improve the quality of the oxide then, but still these mechanisms such as CS, CHE or FN will definitely stress it. And however high quality insulator you make, the moment you start forcing current through it, its quality will degrade with time. Its quality will degrade with program erase cycles, and it will definitely lead to SILC, and retention after cycling will definitely be a problem. So this kind of finishes the discussion about the reliability of flash memories.